let's start from the top of the chapter and read through to neural network policies and evaluating actions, the credit assignment problem. So if we can finish the evaluating actions, the credit assignment problem, uh, that's approximately. So I have gone through this and I do kind of uh, I know my way around this chapter. Uh, I don't know if for you guys, for the first time readers, how easy will it be? But uh, yeah,
Let's give it a
6092.
try. Let's give it a
Yeah.
try. How long do you want to spend on it?
50 minutes. If
Yeah,
not, then we
sounds
can
good.
extend it by 10 more.
Sounds good.
Yeah. Yep. So let me share my screen and we can be at 11. Yeah. Cool. Let's begin. Hey guys.
Hello.
So, have we finished the credit assignment problems? The reading till the credit assignment problem. So, I just wanted to get overview of the folks. Uh, mm, how comfortable are they with the credit assignment? So we can discuss it till there, or take the other heading too, the policy gradients.
I'm fine till credit assignment problem. I read that section. That's fine.
Okay, cool. So we will discuss it too. Uh, mm, Let me try to share my screen first. I hope you can see my screen.
Yes.
Okay, so let's start from the top. Here we go through the reinforcement learning, and in the first paragraph, the author discusses the many interesting applications uh, with respect to the games. Here we are referring to the TD Gammon backgammon playing program that was introduced in the 1950s. So TD Gammon, this is the TD Gammon. Uh, so we have white checkers and black checkers here, and the opponent has to uh, uh, take the pieces of uh, the player that he's playing against, and there are rules to it, and this game has been analyzed, and uh, mm, this is one of the oldest uh, how do I say it, the board games that were first solved by reinforcement learning. And this was and uh, uh, done using the temporal difference learning uh, with I think so. This was introduced in 1995. So this is the 1995 version in which they use TD methods. But this I wanted to give an overview of what this game looks like, and uh, it's a um, how do I say it? A very common game that's been played. Uh, then this TD Gammon was uh, this application that uh, solved this. Firstly, in the machine control, and it made the headlines. The advantage of this method was since if we this compared if this was compared to the chess games that were solved using reinforcement learning, or using the high level uh, deterministic algorithms, then this is a problem in which uh, the weak positions has the strength in the battle. Uh, with respect to suppose you need here specifically in this game, you have to have some sort of a pattern that is associated with it. Suppose if we look at chess, so there we have 64 boxes, and uh, uh, those white pieces and black pieces have a specific pattern to it that has to be placed. But here, and the strength there depends upon the specific patterns and how can we solve those patterns in or break down the opposition patterns. Here it depends upon the variance about of the uh, particular uh, uh, game, the pieces in the particular game. So this game has uh, uh, effect. This game affects the variance of this game is solved using the TD approach, in which the variance is given a specific higher, how do I say it, strength as opposed to those closed patterns that are in a chess. So those judgments, those policies that were made, and those rewards that are collected are based upon the strength of the variance in those pieces. So that was one of the uh, uh, insights of this research paper versus the this TD Kamen approach versus the chess approach. So then moving forward, uh, in 2013, DeepMind demonstrated that the system could learn to play just about Atari game from scratch, even outperforming humans. Here they have uh, a couple of, I think so, 5 or 6 games that they have solved, and most of them were solved using the raw input pixels and without any prior rules of the game in which they were trying to solve it. So uh, these are the 4 games: Atari 2600, the Pong one, the Breakout, the Space Invaders, the Sequest, and the Beam Rider. These are the five games uh, in which they solved this. Uh, and the visual input was, if we go into the research paper, that yeah, they have detailed their deep Q learning approach and what was the algorithm that I used. We will go in this in the next section, I suppose. Um, uh, in 2016, AlphaGo with Lee Sedol, uh, which was the first victory which they uh, uh, played against and won. And it was the master that they the professional player that they beat, and from then on they have been uh, how do I say it, improving their uh, alpha go and alpha series of algorithms uh, uh, to master chess, shogi, and other games too. And a recent paper also came out in December, I hope, in which they solved a more generic class of uh, a single algorithm that solved a more generic class of problem. They solved 4 games, I think. Let me quickly check it out. Yeah, Mu Zero, mastering Go, chess, shogi, and Atari without rules. Yep. So here since they had self-play here, this is, I think so, Alpha Zero, and this came out, yeah, in December, which they solved Go, chess, shogi, and Atari, uh, uh, and allowing it to master the environments with unknown dynamics. So single algorithms could be generalized to these four, which is a big thing from a reinforcement learning perspective. If we look at the evolution of AlphaGo, with Go having the human data, domain knowledge, and the known rules, then the AlphaGo Zero uh, with only the known rules, then Alpha Zero with Go, chess, shogi that solved these three with the known rules, and Mu Zero which solved these four: Go, chess, shogi, and Atari with unknown rules and unknown dynamics. That was a big leap that they took. I will share this link in the chat. Quickly do it. Yeah. Chapter. So this is the alpha series of the DeepMind, in which how they generalize this. Next, yeah, they were bought over for 500 million, yeah. And in the second paragraph, they had given explanation of what reinforcement learning is and what it is good at, and what are the two most important techniques with respect are. What this book summarizes, that's the policy gradient and the deep Q networks. And the MDPs are the basic building blocks of uh, uh, any reinforcement learning based uh, application, or and there are multiple variants of MDPs that if you go into research, then you will take a look at and try to implement that. I do it, so I have a few variations of MDPs I try to play around with. Then they have introduced the TF agents library, which is related to TensorFlow. And they, in the end, they have tried to play Breakout game, the famous Atari game, and closed it with 6 algorithms, I think so, which are in the end, and we will take a deeper look at those algorithms. We will spend sufficient time with each one of them. Then the second heading here is learning to optimize rewards, in which the author talks about a software agent that makes observations and takes actions within the observation and returns its received rewards. So what this is trying to maximize the rewards over time. And here there are two things that have to be kept in mind. One is the reward, and the other thing is I think so. The word is the summation of all the rewards. I always get confused between them. I think so. That's called the uh, uh, return. Yeah. Uh, uh, Here, rewards can be thought of as every action at every time step that a agent takes, and return is the sum of all the rewards that are accumulated, and then they are added to uh, a particular agent's uh, expectation of the policy updates, and then those policies are updated based on that, and there are multiple algorithms or multiple frameworks to do the same thing, and that is when we optimize or apply some sort of prioritization or greedy approaches to take those rewards and uh, kind of sample it in a way that is easier to how do I say it? Or easier to implement uh, uh, over time with respect to the uh, uh, time and the space complexity that we can bound our algorithm with. This is one of the practical insights of how we think about in those perspective and try to implement it. And here, the agent has the act in the environment, and they have given five different environments. The first is the robotics. Second is the Pac-Man, 2D board game. This is a complex environment. Uh, the third is the Go player. The fourth is the thermostat, and the fifth is the trader system, the stock market. Uh, these are the five examples of where reinforcement learning could be applied, and how uh, can we formulate our MDPs into. We will study about how we can formulate our MDPs into the set of these problems, uh, and such that we can decompose our high level problem into the set of those six parameters: a state, action, time space, the next state, the reward, and so on. And here we have other examples in which the reinforcement learning is well suited: self-driving cars, recommender systems, placing ads on a web page. This classification should focus its attention. Also, bandits. Bandits are one of the approaches that are being used nowadays in the industry, and multiple algorithms. Since this book hasn't covered bandits, but I will give a brief one or two liner. They are also being used here with respect to those same recommender systems, placing ads on the web page, like the A/B test that we see, and the image classification too. And there are three to four more interesting use cases of them, which are currently being optimized which are currently being utilized in the industry. Uh, so that was a basic introduction. Then we go on to policy search. The policy you can think of is they've defined it here, the algorithm a software agent uses to determine its actions. Uh, Policy you can also think of in other terms as uh, a set of as we have in this figure. If I try to expand this figure, so here the cloud here represents the policy in which this is a three-layered network. The input comes in, and a set of dense layers or fully connected layers, and the actions are being taken with respect to the environment. Here they have represented a fire or a bucket with respect to water being poured in. An agent performs an action. Here, this may be a robot which performs, which takes of an action of igniting something if the on the inputs of a particular policy, or pouring water over something if there needs to be some fire that needs to be how do I say it? Yep. Uh, so, but here they have also given a great example of a robotic vacuum cleaner, and those parameters with respect to how those probability of P, which can be uh, uh, calculated. Here they have, with respect to that particular robot, we have the probability P of every second, and the rotation of the left or right, and this is the P, and the random rotation is given as the probability 1 minus P. So, and the rotating angle, if we take a look, if you guys have heard about Roomba, uh, it's a basic algorithm which you can think of in that way. Uh, that robot that cleans your house. So that there are two parameters here, the P and the R. Uh, and the R is the random angle the your robot will rotate if we are trying to look for a space in which it has to go. And this also involves some randomness because a noise is being inserted, or and, this may be called a stochastic policy here. And the robot uh, and the problem that they are trying to solve is how much the dust it will pick up in the 30 minutes. That robot can go around the same path and rotate, or have a curiosity-based approach in which in which more noise is being inserted and it does not follow the same path um, again and again. So that's a problem that this policy search attacks on here in this particular uh, robot vacuum cleaner environment. And then an intuitive idea of how will you train that robot, since there are just two policy parameters, the probability P and the angle range. Uh, mm, so what they have, the author has given an example for policy search with respect to those P and R parameters. So imagine this is the policy space A, B, C, and D, and R is increasing here, and the P is increasing here. The P is a probability, and the angle range of R. Angle range is R. So uh, how do we optimize our P and R in a way that maximizes our chances of collecting the most dust in 30 minutes? And what should be the good set of parameters be like here? So here they have given kind of a visual uh, pathway as to how, if the angle range is more and the probability is less, so it will try to move more. Yep. And the A part, uh, since P here represents the rate of going forward or backward, and R here represents the rate of rotation. So this is the random rotations. This case will have those random rotations, which have much more effect, and these two cases will have those higher uh, forward. How do I say it? Those higher forward uh, and uh, the moving forward probability, the stride at which they move before that uh, angle is being rotated. So you can see from the graph here. So this is it here, what they have defined. And the other class of explore the policy space is in this paragraph, they are given a genetic algorithm in which suppose we have a first generation of 100 policies and try them all out and then kill the 80 worst policies and then take those 20 survivors and produce four offsprings, and then an offspring produces a copy of its parent plus some random variation. This can also be thought of as an evolutionary approach perspective, uh, in which this a kind of similar thing happens. Uh, then they can iterate the policies through the same way again and again and come up with the best offspring after suppose 10 generations, which solves that particular problem in the most efficient way or which collects the most dust. And then we can also use the optimization techniques with respect to evaluating the gradients and the rewards uh, with respect, and then updating those gradients and backpropagating it to the network. And this will be discussed in policy gradients, and there are multiple ways of approximating these approaches. Yeah, we will have a discussion there. Then uh, we implement a popular PG Gotham TensorFlow in inline. So any questions till here? Because this is important. This is the basic way to understand what a policy is and what policy space is and how we formulate it in how we intuitively think about it. Yeah.
One question here. So policy space is the, it's not the different kinds of policies by themselves, but the different possibilities
Yes.
of what a policy can include.
Yes, it
So
is.
which means A, B, C, and D are starting points.
Policy space here is a different variation of a problem that can be classified in one of these four objectives. So think of it as if we have those, think of P and R as hyperparameters. Okay? And if we change them, if we have P and R at this point, we try to
Okay,
yeah.
I think I get what you're trying to say. Fine.
Yeah. So if it's 1, if it's 2, here P, and here it's 1 and it's 2. So yeah, we can have a
so the main thing is that the policies can differ with respect to where they start as well as what they actually tell you to do.
Yeah.
Mike, do you mean P and R are parameters or hyperparameters? Because I thought we were
Yeah.
learning these things, right?
They are hyperparameters. Yeah. And it gives an intuitive explanation as to how to think about P and R here.
So P and R is what we learn, what we learn by through different iterations, or is it what we set?
This is what we said.
Okay.
Yeah. Other way to think about this is here. It may be a bit out of context here, but yeah, since I've gone through this book, I remembered this figure. What it is just will give a simple overview approach of what Monte Carlo, exhaustive search, dynamic programming, and temporal difference learning is, and how the width of the update and the depth or the length of the update effects are uh, uh, the dimension of the policies that are being updated with respect to the value iterations. So after a policy has been selected, suppose with respect to P and R, suppose you have selected D here, okay, and after that, what the next step is, or the one of the next steps is to determine what kind of learning or approach that we will use. So this here comes into picture with respect to if we start from the top left here, the temporal difference learning. So that's the simple one step into the future that policy will look for. Then as we increases the depth of the update, uh, and then we have a Monte Carlo solution here. And if we try to increase the width or the variance of where our robot will look for in the problem space, then it's the dynamic programming. And if both the depth and the width are set to maximum, that will be an exhaustive kind of a search in which every uh, uh, state action pair is being looked at with respect to the searches that are need to be that with respect to the searches that need to be performed. So this is advanced a bit. We will take a look at it in the fourth section, I suppose. Yeah, yeah. But I wanted to give an overview about how to think about this with respect to those updates of uh, the slices that we have, and there's yeah, the dimensions, and yeah, this is the backup. Okay. Yeah, you can take this. And then this is the generic algorithms, the evolutionary beta approach, and we have introduced to OpenAI Gym. And here, what we have is a simple real world environment that the Atari simulated constructs, as we have seen here. Yeah, these are the five environments, and there are multiple environments that are available using PyBullet, Mujoko, or many of the 3D simulation environments. There are too many to count. And recently, Google has introduced world models, which is originally based on, if you guys have know about the David Haas world model that came out in NeurIPS in 2018. So that's a new environment that recently came out.
So for
Mhm.
something custom, something very specific to a certain business or a domain,
Mhm.
I guess we would need to build our own simulated environment, right? Or
Yes, yes.
okay.
Mhm. Yeah, we can do that. There are multiple approaches to it. Uh, if you need to build a self-driving environment, you can use Calra,
Mhm.
and that is based on the Unreal Engine, and you can add your own pedestrians, your pathways, your own cars, and your own obstacles. If you're trying to build up uh, a self-driving based navigation environment.
Right. I was thinking of something like training an agent to write programs, for example, right? In like to code, to start like coding, given a certain objective, start
So
coding
that
POC.
okay, okay, okay. So that will be a language-based objective.
Right.
Uh,
Yeah. Yeah.
yeah. So yeah, I have a survey of reinforcement informed by natural language paper here. I think so. I'll share this link. Uh, Maybe this will help.
Okay.
Called the tabula rasa with respect to the vocabulary of the closed world tasks and how do we think so they have also defined they have solved this text corpora in the wild. Yep.
Mm, mm.
Yeah.
Nice.
So yeah, this is yeah.
Thanks.
So no. So these are the 2D and the 3D physical simulations of OpenAI Gem Kit that we can compare and develop new RL algorithms on. And this is the simple installation strategy. I think so. If you get stuck, you can find forums or you can post your queries here, and we will be readily available to help. This is simply making a cart pole V1 environment. Uh, we just call, you just have to make, call a make method, pass in a string, and then you will get 4 observations. Uh, these 4 are respect to uh, velocity, angle, angular velocity, and position. So these are the 4 parameters here that we get. 1, 2, 3, 4. So, and we perform updates based on these 4 parameters in this cartpole V1 environment. Uh, so they have given this in detail here. The NumPy array that contains the 4 floats. Then if we have render, then this will be rendered. They have given XVFB X server, the fake X server that can be used to display it using if you're displaying it in Python, then you have to use a PyVirtual display libraries. You just have to run this and at the beginning of your Python code, and yeah, this will be visible. What they have done here is set the mode as RGB array and to render it as this size here. Then uh, they ask the environment as to what actions are possible. Here they will give we will get a reply of discrete 2, which means that the possible integers. The action space here is 0 and 1. which represents the accelerating left as 0 and right as 1. Other environments have different action spaces and so on. So here, what we have is the OBS in which we have set our action to 1, and we have given the step as action 1, and then we have gotten the 4 parameters here with respect to the observation, reward, done, and info. Reward, done, in info, these are the parameters that we get, and they are printed here. Then the step returns these 4, and it gives us what the observation, the rewards, the done, and the info environment is. We can take a look at it, and it's pretty much easy for the audience that we have here. So I won't go into the detail. Yeah.
I have one question, Mac. Is the initial returned value to be ignored? Because what it confuses me is if you go back up to the first set of 4 values that the reset returns, it says that it's moving, not this one, the one before that, because here we have moved right. The very first set of 4 that it returns right there. There, it seems to return that it's left of center, it's moving left, therefore its angle is greater than 0. But then why is the angular velocity negative? Wouldn't you expect the angular velocity also to be positive if it's moving left? And if so, is it the case that because it's the first time that it's returning something, you ignore that? I was confused by the slightly negative value of the 4th point there.
The angular velocity can be negative if you push to the right. If you accelerate to the right enough, that will force the pole to reverse its direction.
Yes, but in this case, it says that it's going left because
the second value the pole is still leaning to the right, but now you've accelerated to the right, and so it's now starting to move towards the left, so that the angle will be closing towards vertical as you observe it next time. Does that make sense?
I'm missing something because it's saying that it is accelerating left according to the second value of this observation. Second value of the array says that its velocity is towards the left. That's what the negative sign in the second of the array things says. So if it's accelerating left and the angle, so the angle is right, meaning, it's to the right of center, but while accelerating left, its angular velocity is negative.
So
it means it's moving in the same direction.
I think I understand the confusion. When you look at the second, value, that it's negative, that means not that it's accelerating left. It means that it's moving left. There's a difference.
Yes. Okay.
So it's moving to the left, but it's but it could be, I think it's accelerating to the right. That is, it's slowing, it's moving to the left, but it's
moving to the left while slowing down.
Yes.
With less velocity, therefore its thing is swinging to the, okay, that might explain it, but the book doesn't do a good job of giving that, or it doesn't talk about it at all. And that threw me off as to why, when you're moving left, can that last value be negative? But yeah, if it's slowing down while moving left, then you're right, that can be.
Yeah, and since it is an episodic case, so every time we call an environment reset, I think so we have a range of these 4 values that our environment can start off on. So at each start of an episode that we have used a loop here, I suppose, to calculate. Here for episodes in range 500. So for 500 episodes, we are resetting it every time. And yeah, those initial values will be a bit different. I think so we can.
Sorry to interrupt, Mike, but Joseph, the thing that confused me is he then says, right, if you stay there, Mike, for a minute, he says, let's, oops, sorry, go down, please. Right there. Let's hard code a simple policy that accelerates left when the pole is leaning towards the left and accelerates right. And if the 0 or 1 says that it is acceleration, then, and not just velocity as we discussed, then that thing doesn't make sense all over again. You see what I'm saying? If he just said, let's hard code a simple policy that says the velocity, then I would agree with you, because then the acceleration, but he actually says accelerates left by giving it a 0 and accelerates right by giving it a 1.
Yeah. So in this case, the thing that might be confusing is the acceleration is not one of the variables that's shown. It's just one of the actions. And if the pole, in this case, the pole is leaning to the right, correct? Its angle is greater than 0.
Right.
Okay. So it accelerates left when the pole is leaning towards. That seems to be the wrong policy. Maybe he means the other way around.
Is he trying to balance the pole?
Yes. Yeah. If the pole is leaning to the right, I think that makes sense. That makes sense. If the pole is leaning to the right,
makes sense. The policy makes sense to me. But then that's where I'm confused by how, if the second value is in fact acceleration, not velocity, as we discussed, because he says if you have a policy which says 0 or 1, then your acceleration is to the left or accelerating to the right. So if we go back to the first set of 4 values, a negative value on the second item of those 4 says that it's accelerating to the left.
No. The second item is the velocity. The thing that's confusing is that it doesn't show the acceleration as one of the 4. You never get to see the acceleration. All you get to see is the velocity and the angular velocity.
Okay, so it is still policy is acceleration, but the value is velocity. And so when you implement the policy, then in that case, it could be that it's going left, but it's slowing down. Therefore, the thing is negative. Okay, got it.
Yeah, actually, it makes sense because we cannot control velocity directly. We control velocity by changing acceleration. But the observed values are position and velocity. We don't observe acceleration, but we cannot just manipulate velocity like in real world object, right? We manipulate acceleration.
Yeah.
Mm-hmm. Yep. Yeah, so these are the 4 parameters. These are the updates with respect to the revolts. This oscillates left and right until the pole tilts too much. This is an iterative approach. So then we look at the neural network policies here. Since these policies are hard-coded based on those particular values that we return, that is 0 if angle is less than 0 or 1. So we have hard-coded here. We would like to this neural network to take an observation as an input and an output action to be executed with respect to those estimated probabilities. So here, instead of hard coding, we have a multinomial sampling in which we take a particular estimate of a probability into account, and then we take the action based on that. So in the cart pole, we have only 2 possible actions, and the probability of action 0 and the probability of action. If we consider the P as the probability of action 0 and the probability of action 1 right will be 1 minus P. So if the this output is dynamically taken as 0.7, then we will pick the action 0 with 70% probability, or this one action with a 30% probability. So this is a way to dynamically apply probability-based sampling to it. So here we have considered the neural network policy, in which we have a set of 4 inputs, the time steps, or the 4 previous inputs. These are the hidden SELU layers, SELU activations that are followed by the sigmoid, and then they are uh, um, sampled, and then the action is being taken. This approach, why is this being done based on the probabilistic approach given by the neural network? Because it helps the the agent in finding the right balance between the exploration versus the exploitation problem, which is common in RL. And, Mm. Uh, if we double down on that, so exploration will try to search new pathways or new trajectories to solve a particular problem, and exploitation will try to be on the same path. Uh, that then you yep, that will be optimal, but uh, with respect to those constrained predefined paths that you had, but it won't search for a new path way to achieve your objective. So here they have given uh, dishes, the restaurants, and the first time, and uh, uh, what is good dish, and how you can explore every possible dish in the menu, and uh, which must be tried, or uh, some might be even better than your favorite in a particular restaurant. So that's the approach that they have taken here. And then in this particular environment, the past actions and the observations can be safely ignored, since each observation contains the environment's full state. So here they have given uh, uh, since on this particular environment, so they have talked about the card pole V2, uh, in which the past actions and observations can be ignored, since each observation contains the environment's full state. Okay, yep. Uh, uh, since we have the angular velocity, the acceleration, yeah, and each point in the time step has all the 4 parameters here. So that's what it talks about. The other example they give is when the observations are not noisy. In that case, we generally want to use the past few observations to estimate the most likely current state. This noisy observations are with respect to uh, a certain noise or randomized adversarial attack being done at each time step in one of the 4 or all the 4 parameters. So the observations that we get are new or are not truly deterministic in nature. So that's one issue which can be solved using uh, mm, uh, taking those past few observations into account and trying to estimate the most current state. So this is a simple problem. Therefore, observations are noise-free and they contain the environment's full state. So that's And this is the layers. These are the two dense layers. As I have alluded to earlier, this is the ELU activation here. In the five, in the number of inputs is 4 here. 1, 2, 3, 4. The dense is 5. The number of inputs is 4, and the action that we get and the act using the sigmoid is 1 in the end. Yep. That's the whole network that they are putting. And this is a sequential problem. So that's that here. Then we go on to the credit assignment problem. So since we have calculated the best action at each step, if we knew what the best action at each step was, we could train the neural network as usual by minimizing the cross entropy between the estimated probability distribution and the target probability distribution. And they have uh, used this to simply give guidance to the agent to get through its rewards, and which are typically sparse and delayed, because at every time step one agent might get a reward, but of those particular actions that has to be taken. But if we take this cart pull uh, balance for 100 steps, then how can we know that which of the 100 were good or which of them are bad, and which uh, pole fell at the last action? So the last action should not be entirely responsible. And here there's a class of MDPs, that's POM DPs, partially observable, in which we use this. Uh, so it will be MDPs. This is used in some games, Atari games. And this is a kind of a credit assignment for problem when an agent gets a reward and it's hard to act. It's hard for it to know which actions should be credited or blamed for it. And the think of what's being rewarded. A simple robot example that we looked at earlier with respect to the cleaning or the dirt that it can collect in 30 minutes or so. That's that. So we have a common strategy that can be used to sum all the rewards, which can be written as the summation of the discount factor multiplied by the rewards at each time step. So that equation will be, here they have not used that. Yep, the overview of how that equation is being written. So yeah, this is normal equations. Yeah, this is the discounted return that we give. So this discount rate gamma that we have defined here is between 0 and 1. This discount factor, or the discount rate as they have used it here, and it's the the return that we give is the r of t plus 1 into gamma of r t plus 2 to gamma square of these guys here, which is described as a summation of k from 0 to infinity gamma to the power k r t plus k plus 1. That's the discounted return that these um, text talks about. And they have given an example here as to if we have a discount factor of 0.95, if we take, and the rewards are 13 steps into the future. So at the 13 steps into the future, those mm, the weights of that particular that immediate report at the 13th step will have a half impact. That is, that will be roughly half the immediate rewards that are calculated at that particular time step. So it will be multiplied by 0.5, which is a simple series equation here, if we look at it. So yeah, so this is the formulation in simple terms. Actions, right. Then rewards are +10 here, 0 here, and -50 here. And the sum of the discounted future rewards are -22, -40, -50 with respect to the discount ratio, 80% and 80%, which is being applied here. So this is how this return is being calculated. And this the issue with calculation of this good action that is being suppose if here, yeah, they have given a very good example that suppose we have a good action that is followed by several bad actions, and we initially had that good action that has to be taken into account. Yep, with respect to suppose this, right? And how can we sample our trajectories in such a case that in uh, suppose here to only one action is right, and if we look at if we extend this problem to 50 or 60 or 100 suppose, and at you may have a series of uh, good actions, and then bad one that has -100 or -50 error discount kind of, which totally gives the your return a lower value, which it does not sample from, and those trajectories are not taken into account. Their POM DPs come into place. Yeah, uh, uh, that's called an action advantage too, and we can kind of normalize it based on the how many episodes and action returns on. So we can have some sort of, how do I say it, formulation of how we can randomly take that sample or a set of uh, actions that are good, and then this kind of a action advantage strategy can be applied. So yeah, these are a combination of two approaches that I'm trying to intermingle. But yeah, I think you get my point, and I will love to have some queries here. The example that I talked about was Montezuma's Revenge. This is a very good game in which suppose the in which the POM DPs are. I just remembered it on the top of my head. There was a presentation by DeepMind that I attended in which we talked about this stuff. And you can find the implementations of this online too. So I'm just sharing it. That. So this, I think so the time is up too. We have covered it until this point. Any queries? Yeah, please fire. Please fire queries. Hello, can you guys hear me or?
Yeah, we can hear you, Maya.
Okay, cool.
Hey, Mayank, could you let us know what is that book that you're displaying on the left?
That's the same book that this has in the link in the
It's
end.
This is Satman Bartu book. Yeah, it's
The,
available for
Sakhiram.
free.
Oh,
Yeah.
okay.
Yeah,
thank you.
That's the same book. That's the first. This is
Let's see. Terrence has a question about the notebook, and let me see. So, Terrence, you're saying that you run the notebook and it's not completing, or for you?
Yeah, that's exactly what's going on. I ran, I used to just run through the notebook to see that it's a clean run.
Yeah,
and at
yeah,
that
yeah.
particular section, I guess where they're, working on the beat breakout section.
Which section is this? Introduction.
It's way down in the notebook, but it's TF agent environments where that's being created. There seems to be an issue.
Q is below Q learning.
It is.
I didn't get that far yet, but
no. What was the error here? So if you can
let me see if I still have it. I may have rerun it, and it could take some time to get there. It was a JIT compile issue. I should have saved it before I deleted the notebook to run it again.
Which line threw the error?
The line, let me get back to it. The from clause from TF underscore agent, environment through the error.
Let's see.
Let me see if I saved it in another notebook. No, I deleted the notebook. I should have saved the error at least.
Do we have to install something first? Do we have to install TF agent somehow, pip install or something?
It's done at the top of the notebook.
Ah, okay.
Yeah, it does some dependency checks, and then it actually installs. But I mean, if you haven't gotten to that section, I mean,
I'll make a note for myself that you saw that and see if what happens when I get. I'm not that far down in the notebook yet, but
okay.
Yeah, I do the same thing you're doing, is just running it through to make sure that it runs.
Correct. Okay.
Maybe you need to install TF agents.
Yeah, and then what I did is once it broke there, I actually tried to run TF agents, and then I got issues because if you look at the very top, well, you know what? I may not. At the top of the notebook, I guess 4 or 5 lines in, there's a try statement where it does a pip install of TF agents -nightly.
Yeah.
So I'm not sure if it ran that or not. Maybe it didn't.
Yeah. Or you can pip list it in the command prompt. And
okay.
You can also see the result there if TF agents is there in the set of packages that are listed.
Okay, I'll give that a try. But you know, that's way down in the notebook. Nothing else seemed to have had a problem until it got to that portion.
Okay. Cool.
So maybe others are running into the same issue. If once I'm running through it again, when I get to that point, I'll go ahead and try another pip install of it just in case and see if that gets me through. Thank you.
Yeah, I'll try it too and see if, what I get.
So that's it from my side. The next time we will discuss policy gradients based on a reinforced class of algorithms, and how it follow the gradients towards the higher rewards. With respect to the factors that we discussed earlier, and how we normalize it and how we optimize those certain gradients. With respect to here, we have, I think so, given the mean. With respect to those mean, and simply we have taken the updates, but we can have some sort of a Bayesian approach to it too. Bayesian variational inference, in which we can apply that. Or there are other ways to sharpen the trajectory based on the task that we have in account. And then we will discuss about the Markov decision processes. Yeah, if possible, get a here they have described the 1950s by Richard Bellman, but I think so in 2015, in Europe's 2015, they gave a great. I will share a video for the introduction to Markov decision processes and the various factors that you have, and the variations of them. It's very much interesting to get into the details here. Then we will discuss the Bellman's optimality equations, value iterations, then the temporal difference learning, the Q learning, all that stuff. So this is exciting. Stay tuned for the next iteration on Sunday.
Definitely. Thank you so much, Mike. We really appreciate your leading us in this, because I think you're the only one that really has some experience in this area.
Cool. No issues.
Okay, we'll see everybody on Wednesday.